Well, good afternoon, everyone. I think we should make a start. It's a real pleasure and an honor to welcome and introduce Professor Vaidhyanathan Ramamurthy as our WIN seminar speaker for today. Professor Ramamurthy had his early education in India before moving to the United States for doctoral and postdoctoral work. He did a PhD at the University of Hawaii, a lot of people close, with Professor R.S.H. Liu, and followed that with postdoctoral studies at the University of Western Ontario, now known as Western, in photochemistry in the Paul DeMayo group, which at the time was one of the preeminent groups in photochemistry in the world. After a further PDF at Columbia with Nicholas Turrow, he returned to India as an assistant professor at the Indian Institute of Science, IISc, in Bangalore, one of India's top research institutions, and incidentally, an organization with whom WIN has a collaborative agreement. At IISc, he began a research program in organic photochemistry and later supramolecular photochemistry. In 1987, he returned to the United States, working at DuPont until 1994, and Tulane University in New Orleans before moving to the University of Miami in 2005, where he is at the present time, of course. He edited a highly popular monograph entitled Photochemistry in Organized and Constrained Media in 1991 that led to a series entitled Molecular and Supramolecular Photochemistry, which is published in 14 volumes between 1994 and 2004. He has recently co-authored a textbook, Modern Molecular Organic Photochemistry, by N.J. Turrow, V. Ramamurthy, and Tito Sciano, a Canadian from the University of Ottawa, which is used by students and researchers alike in photochemistry and physical organic chemistry. Dr. Ramamurthy had authored 330 scientific publications and co-edited 20 monographs and special issues for various journals. He is, in addition to that, in addition to being a researcher, he has served as an administrator. Particularly mentionable here is as departmental chair since 2004. He also serves as senior editor for the American Chemical Society journal Langmuir, and his most recent honor in 2011 was the Provost Award for Excellence in Scholarly Activity at the University of Miami. Please welcome Professor Ramamurthy.
All right, thank you. Okay, let me first thank Professor Arthur Cartry for the kind invitation and making arrangements for the visit here. My visit to Waterloo is almost 43 years late. If you notice here, in 1968, April 11th, I was offered admission to this department as a graduate student. Let me see.
Good record.
So for the students, I think for the graduate students who might be here, I was offered a stipend of $2,600 per year. Okay, that is, they said, for $200 a month should be enough to live in Waterloo. And then you can see why I went to University of Hawaii. So it is, I was a little bit scared of cold weather and snow, and then Hawaii seemed like quite different from Waterloo. So this is, I still had this letter. It was signed by Professor Rudin. I don't know whether he's still here.
He died recently.
Oh, is that right? Okay. All right, so I'm going to talk about what I call as photochemistry in a capsule. And as already mentioned, I like places which is warm and then not too much snow. This is in Miami. The picture was taken maybe a couple of weeks ago in Everglades. As you can see here, there are lots of birds and variety, different kinds. They are all sitting here. They all probably came from Canada, and then they are all waiting. They may not know there is no snow here right now. So once they sense that weather is getting better in Canada, they probably will fly back. Okay. So what I'm going to talk about is reactions or photophysics or photochemistry in a capsule. Okay. So we will talk as we go along. Towards the end of the talk, halfway through, I will talk about communication between molecules which are inside and outside a capsule. At the beginning, I will talk about a little bit of chemistry inside a capsule. I will tell you what a capsule is to get started. Why we do this sort of stuff. For example, our goal is to control the chemistry of molecules, and to control anything, it is important to confine them to some degree, especially when the molecule is highly reactive, like a lion sit here. So if you put in a cage, they seem to be very friendly. Okay, so they do things what we want. So confining is one way to control the reactions. Okay, the second thing is, I was talking to someone this morning. So geckos, for example, this is research done in this center. They can walk up and down on the roof partly because if you look at their feet, it has got a lot of polymers with which it can make a contact with the walls through weak interactions. And these weak interactions are the ones that make them not fall from the roof to the floor. So we are going to use two of these basic principles to control the chemistry of molecules in confinement and weak interactions. So weak interactions there are too many of these things we study these days. I will mention a few as we go along. Okay, we all study chemistry, from textbooks which are very popular for organic chemists. There are a whole bunch of textbooks. We learn about reactions, we learn about concepts. All of them are based on the chemistry, either in the gas phase or in solution phase. So we have our own mental picture of how the reactions would behave, how the molecules would behave. But if you put the molecule as part of a biological system where the molecule is confined to some degree, then, for example, here, there is a small molecule which is rhodopsin, which is retinol, which is part of this protein. This molecule is very selective when they behave as part of the eye, which is how you see things here. When you put the molecule in solution or the gas phase, it has got 4 double bonds. When we shine light on them, they give 16 isomers, whereas as a part of this protein, they give you only single isomer. That's how we are able to see very clearly. If it gives 16 isomers, you will see a very blurry picture here. So why the chemistry becomes, what we learn from the textbooks, it doesn't seem to be applicable when the molecule is part of a highly confined system. So selectivity increases. So what we want to do is basically duplicate this type of chemistry in a simple approach. We don't want to make all these big proteins and isolate things and then do this chemistry, make it more pretty complicated. So we want to the concept is very simple. We want to put the molecule in a highly confined space. Oftentimes the proteins, they offer weak interactions between the molecule and this protein. Those are the ones which control the selectivity of these molecules in the excited state. Okay? So in general, what we want to do, our goal in our laboratory is, we want to carry out reactions in a medium or any kind of thing, in a medium which is quite distinct from everyday organic solvents, because these days we want to do things pollution-free conditions, so we want to do reactions in water. If we cannot do it in water, we want to do in solid state, that is crystals. We want to take a molecule as a crystal and then do the chemistry of these things. But the problem with this kind of, the goal is, could be noble, but the problem is most organic molecules are not water soluble, and most organic compounds are not solids. So first, to make any progress, you have to make things soluble in water, or most organic compounds somehow you have to convert them into solid. These are the first thing that you have to do. So we can do these things. So we can solubilize organic molecules in water by using water-soluble organic molecules, like soap is a water-soluble thing that we use every day, the micelles and this kind of stuff. Similarly, if you absorb an organic molecule inside solid samples like zeolites, then it becomes a solid as a whole, then you can carry out highly selective chemistry. So this type of chemistry, in a way, to convince people to give money, you have to use correct terms. So we call this kind of chemistry as bio-inspired, green, which is people who want to be pollution-free, supramolecular, this is what we do, and nano, because our capsules are small, and we do photochemistry. So we call it as bio-inspired green supramolecular nanophotochemistry. So we have, it doesn't matter what changes the field, we have the terms here. So we will. So at the end of all this stuff, what we do is basically container chemistry. We want to put a molecule in a small container and then look at the chemistry of these things. So what type of containers we are talking about? Container, again, there are lots of containers. You know, I know some of you have been to India. I have taken some of these pictures in India on the street. For example, there's a whole bunch of containers if you go to. So there are containers of different makes, different size, and different shapes. So, but these containers are not the ones that I'm talking about, but it gives you an idea that you can put molecules in a container, and the container could be different each time. And if you go to United States, you find a container store. So the chemistry of container is not, you know, other people have already patented all this stuff. So they have container chemistry, okay? So what we are going to be talking about is a container which is very small. So this is, you know, you have a center of nano. So all these molecules are nano in a way. For example, the first thing is most of all the molecules listed here, excepting zeolites and crystals, they are all water soluble. So you don't have to do any chemistry in benzene or methanol or acetonitrile or any of this stuff. All of them can be done in water. And second thing is they all can solubilize organic molecules which are not water soluble. For example, cyclodextrins, which is a well-known system. It has a hole in the middle, cucurbitryls, and then calixarenes. All of these things they are water solubles, but they all have a small space, which is about 10 nanometers to 15 nanometers, 15 angstroms, so very small, a couple of nanometers. And you can put an organic molecule inside this hole, and once it goes inside, it will stay there because it will not come out because outside is hydrophobic. And once it is inside, depending upon what type of thing that you choose, you can control the chemistry. And then this, for example, palladium nanocage is one of these things which is also used, which is about a little bit larger than many of these things shown here. What I am going to talk about is only one type of capsule, which is container, which is octa acid. We do almost all of these things, including zeolites and crystals. So today I'm going to talk about mainly this octa acid. What exactly is octa acid? Well, before that, I just want to tell you, it doesn't matter what you choose, whether you choose the cyclodextrins or zeolites or cucurbitryls, they all have the very same features. The features are simply this one. So you can think of this as a container, as a bowl. The inside is hydrophobic, outside is hydrophilic. This whole area is filled with water. So the organic molecule which is here, it will always go inside this one if it is put in water, because they don't want to stay in water. So we instead of calling them containers, you call them as a reaction cavity, and this is a boundary. For example, micelles has a boundary. If you have a cyclodextrin, they all have well-defined boundaries between this water and the inside. And then you put a guest molecule inside, and the guest molecule, when it occupies, you have to choose the right container or right host system. We call them in a different way is host-guest molecule. This is a host, this is a guest. So the guest should fit within the host, and also when it fits, it should leave some small space, and also it should not be completely occupied, it should not be a lot of space. So depending upon this is called as free volume or free space. If it is, yes, it completely occupies, there's very little space, then this molecule cannot undergo any chemistry. If it is very tiny and if there's a lot of space, then the reaction will not be selective. So based on these two concepts, you choose the right kind of host. Some of the hosts you have to make, some of them you can buy, some of them you can get it free. For example, cyclodextrin, these days you can get it almost free, a kilogram, from some of these companies because they make a lot of cyclodextrins from cornstarch. And many times what happens is these host systems, they have some links within the system. For example, hydroxyl groups, COOH groups, or a phenyl group. So what can do is they can build some interactions between the guest molecules and the host systems, and these interactions, that is what we call as weak interactions. That's what I mentioned to you about the gecko or some of these things. So if they have some interactions between these things, then when we activate this molecule, we have to react within the host systems, And they may not want to lose these interactions as they react. So many of these things are going to be controlled by these weak interactions, which may be 2 calories or 5 calories, but still they can be very effective in controlling the chemistry. Okay, these are the weak interactions that you probably study in textbooks these days. These are all few kilocalories. So pi interactions, chlorine interactions, and then these fluorine hydrogen interactions. Many of these things are well known, but it is not very effectively used in chemistry until about 5-6 years ago. So when you do the chemistry in a highly confined space, these things can become very important because the interactions can become stronger and the molecules may not want to lose whatever it has already as it proceeds to something else. Okay, octa acid. This was originally made by Don Cram, published in ChemCom. It is called octa acid because there are 8 acid groups. And the problem with this octa acid, which was made by Cram, is it is very small. It is about, the inside is like less than 5 angstroms diameter. So you cannot put too many big molecules. You can put methanol, chloroform, methylene chloride like that. And the best example that he did was he was able to put cyclobutadiene and make it stable. Cyclobutadiene, everybody thinks is very, very unstable. But he published a paper in Angewandte Chemie and then showed that it can be stored for days as cyclobutadiene at room temperature inside this kind of systems. So the octa acid that we use in the next 40 minutes is this particular one, which also has got 8 acid groups, but it is very similar to this, but only half of it. So the top is open and the bottom is somewhat narrow. So you can put a molecule inside here very easily, whereas here you cannot put any molecule from outside because you have to put whatever molecule you want during the synthesis. The synthesis is pretty complex, and then you have to put the host molecule, the guest, such as simple chloroform, as you make the compound. But here you don't have to worry about this. This is a open system. I will show you a little bit of the size. So the inside of this molecule, it looks like a small cup, and it is open at the top. The diameter is about 12 angstroms. Okay, so it is a very small nano container, and the height is about 13, and then the bottom is about 5 angstroms. So that's why I have put you a structure like this. So this molecule is water soluble. It is soluble in a slightly basic medium, like a borate buffer. You can dissolve this, and when you dissolve that thing, it is all the COOH becomes COO minus. So in the rest of the talk, I will not be showing the structure, but I will show this one. So whenever you see this picture, that means it is this compound. So we call this a host, or you call them as a capsule or a container, or sometimes it is called as cavitand. So they have, depending upon who reads the paper, who writes, they have different names for these things. Okay. First thing is, they form different types of complexes. All these things could be characterized by NMR. This is a guest molecule. This is octa acid host. If you mix these two, even if this is not water soluble, if you mix them in water, this one will form a complex. The whole solution will become transparent. Although this one, as it is, it will not be soluble, so you will see a white powder floating. But then, as soon as you add this one, it will become transparent, and it forms a 1-to-1 complex. That is one guest and one host. This is a nomenclature used for this. Sometimes what happens is, if you have a long guest molecules, part of it will go inside, some of it might be exposed to water. So this is still hydrophobic. So it doesn't want to face the water. So what will happen is a second host molecule will come and close this stuff. Then it forms a 2-to-1 complex. The 2-to-1 complex are the ones we call as capsules. Capsules. So basically, it's like a aspirin in a bottle. So you have this bottom part, another molecule goes in, and then it screws the whole thing. Okay, so it is very tight. It doesn't come out that easily. Okay. All right. So sometimes what happens is, if you have a molecule which is small, then you can form a 2-to-2 complex. The capsule can contain 2 molecules. So it can have 1-to-1, 2-to-1, or 2-to-2. It depends upon what type of molecules you have. So I just want to show you quickly what decides what type of system is formed. Okay, for example, if you take a guest molecule which contains a hydrophobic group, which is adamantane, the hydrophilic head group, then you form a 1-to-1 complex, because this part has no problem in facing water. If you replace this with a hydrophobic group again, an alkyl ester, then it forms a 2-to-1 capsule. That is, 2 of these things, and this long chain doesn't want to face water, so another one of these things will close this stuff, and then it forms this capsule. If you have a small molecule which does not contain the head group, then what happens is it may form a 2-to-1, or if you, since there is a lot of space here, one more molecule can go inside, then it can form a 2-to-2 complex. So it is, first of all, what kind of complex you are going to get depends upon what type of guest you have, and you can characterize these things by NMR, titration experiments, and all these things will, first you can do all this stuff. This is pretty straightforward. To have a feeling for, to get a good feeling for size of the capsule, this is, this is a really nano capsules. So this is, the whole thing is, for example, it can accommodate 2 naphthalenes, 2 anthracenes, tetracene, it can put only 1, pyrene, you can put only 1. Tetracene, for example, if you have one more group, it will not go in. Or if you have a pyrene, if you put one more group on this side, it will not go in. So this is about the size of the capsule. So the capsule is about, you can say from here to here is about 2 nanometers, across it is about 1.5 nanometers. Okay. So very small host guest complex, and these are water soluble, most important of all. Okay, first thing is we have this molecule, the capsule. It is, the whole thing is like a ship in the sea. So the outside is all water, and inside this capsule, are there any water molecules? Because the ship, when you travel, there are no water inside the ship. Similarly, we want to check out whether if you have this capsule, although it is floating in water, does it contain water inside? Because it is very important to know what is the polarity of these capsules inside of these things. So you can do these things, for people who are familiar with photochemistry. There's a whole lot of molecules which are used as probes. For example, pyrene, pyrenaldehyde, and anthracenes, and coumarines, and all this stuff. Each one does a different thing depending upon the polarity of the medium. Pyrene is a very famous example. So what is called as vibrational spectrum of the pyrene emission spectrum, I1 by I3, it depends upon the polarity. If it is acetonitrile, you have one number, methanol some other number, benzene something else. There are tables and tables of these things. So if you record the spectrum, then I can tell immediately, okay, this is like benzene, or this is like acetonitrile. So we have put all these molecules inside, and then recorded the emission spectrum, or recorded the lifetime, and then we got the final conclusion is, so the capsule contains a pyrene, outside is all water, inside there are no water molecules. The pyrene is sitting inside the capsule. Although it is all in water, the pyrene, as far as pyrene is concerned, it does not know there are water molecules surrounding this capsule. Okay? That is something basic. Okay, this is a very common thing with all the molecules that we study. Okay, what I want to do is I want to give you a couple of examples how you can control the chemistry. Then I will talk about a little bit of EPR spectroscopy. Anthracene. This is the ancient photochemistry. Photochemistry of anthracene was studied in 1860s and 70s. A lot of work was done in Europe. Anthracene is very well known to dimerize. Okay, the quantum yield of dimerization is almost 1. And then a lot of molecules show what is called as hexamer emission. Before they dimerize, they will show hexamer emission. Anthracene is an odd example, which does not show any hexamer emission in solution. So this has been, people have studied this compound for years and years and years, and then they were never able to see hexamer emission, but because it was always dimerizing. Okay, this is the standard thing. Our goal is, can we reverse this chemistry by using these capsules? Okay. Okay. For anthracene, it's not water soluble. If you put anthracene in water, you will see white powder floating. Okay. But now, if you add this compound, the solution will become transparent, and then you can record the NMR spectrum very clearly, sharp peaks. So here is the NMR spectrum for anthracene, and this one both in solution and aqueous solution. And if you look at this NMR, there are 5 peaks for anthracene. 1, 2, 3, 4, 5. All these marked, and the other peaks correspond to the host peaks. Okay, anthracene. Some of you who might have recorded NMR spectrum. Anthracene peaks are supposed to come somewhere between 7 and 8. But if you look at this, once it goes inside the capsule, it is shifted to 3 and 3.5. It is shifted all the way upfield. Okay. That is one indication this molecule is not free, it is stuck inside. Because inside, as I told you before, it contains a lot of benzene groups. So when the molecule goes inside, it will feel this deshielding by the benzene rings. So that's why it is shifted to upfield, way upfield. Okay. And then more important thing is, normally anthracene should give you only 3 peaks, 1, 2, and 3. Everything else is repeat. Okay. But if you look at this one, it contains 5 peaks. The regular anthracene, once it goes inside, it seems like it is an odd NMR spectrum. Okay. So one way to sort out this problem is you can do COSY NMR, and then we know all these details. I don't want to go into the details of all these things. So you have got 5. Suppose you have half molecule buried inside, the other half is facing water. So now all these peaks are different. So now you have got 5 peaks. But the thing is, if we do what is called as nuclear overhauser effect on these compounds, if you look at this number 1 and number 5, they are close to each other according to the NOE experiments. Number 1 and number 5, they are far away. According to, if this structure is correct, then they cannot have very close correlation. That according to the NOE means they are very close. Otherwise, you don't see NOE signals. Okay. Now, the only way you can accommodate all these things is you have 2 molecules inside the capsule, and the 2 molecules, one anthracene, another anthracene, they are slightly offset from each other. This is number 1 and that is number 5. When you flip this molecule, this becomes number 5, that becomes number 1. So now if you notice, number 1 and number 5, they are close to each other, and because of that you see the NOE. Okay, so this is, you can do a lot more other experiments, and we can confirm that what we have is 2 molecules inside the capsule. Okay. Now, this much is, next part is what happens to the chemistry. Okay, anthracene in water, and then when you have anthracene in water, which is very, very dilute because it is not soluble, what you see is monomer emission, fluorescent spectrum, which is very common. Now, if you add the octa acid into the solution, as soon as you add, within a few minutes, you will see the solution will become transparent. And if you record the emission spectrum, you see the fluorescence, and also you see a very strong Xemer emission. As I told you before, Xemer emission of anthracene is unknown. Okay? Lots of people have tried this emission before, and a number of very important people, they spend a lot of their time, including people in the industries, because anthracene, in those days was 1960s and 70s, there were a lot of interest in using these kind of molecules as to record photolithography type of stuff. Okay? But now this molecule is emissive and it has a very long lifetime, and the dimer of these things is very close to the one what is in crystals. You can get the Xemer emission. So the chemistry of these capsules are somewhat similar to solid state, because the 2 molecules are stuck inside the capsule, they don't move, and then you can see a strong emission. But now the chemistry wise, you remember I told you before, in solution it dimerize and then no Xemer, but inside the capsule it is opposite. There is a very strong Xemer emission. If you keep irradiating, there is no dimers. So the chemistry is completely reversed from solution to the water in the presence of capsules. Okay, the reason for this is because if you have 2 molecules, it occupies some space. If you dimerize it, it is going to get bigger. If it wants to get bigger, the capsule is smaller than this molecule, so it will not allow it to dimerize. So because the cavity is very small, is about 15 angstroms across, but then if it wants to go bigger, then it cannot accommodate that, so there is no reaction. Okay, so this one tells you that when you do the chemistry in a nano, medium, then it can be completely quite different from what happens in everyday thing. I will show you one more example, and then we will move on to somewhat more physical. Okay, this is another type of chemistry. Okay, so this is a simple reaction. This is often used in organic synthesis, reactions of single oxygen with alkenes. So these types of reactions are called as Ene reactions. you take the olefins, you take the oxygen, and then irradiate with in presence of a sensitizer. You will produce single oxygen. Single oxygen will react with a double bond, and then it will, when it reacts, it can abstract this hydrogen, or that hydrogen. Depending on which one of these hydrogen it abstracts, you will get 3 products. You know, some of you might have studied organic textbooks. Most of the time the reactions are messy, and then especially photochemistry is even more messy. So what happens is, if we irradiate something, you will get 5 products, 10 products, so that usually people give up. So, but so here, in principle, you can get all 3 products in solution, because oxygen is a very small molecule. So there is not going to be much of a difference whether it comes from this side or from that side, and whether it abstracts this or that or this. It is all equivalent. So you will get all 3. And in fact, that's what happens in solution. Published by Chris Foote in 1970s. So what happens is, you get all 3 products. Now this is the same kind of systems, so you get a mixture. Now the question is, can we control the chemistry by putting the molecule inside this small cavity? Okay, first thing is, by this time you know, when you put a molecule like this, this kind of molecule, once again, is not soluble in water. But if you put the molecule and this cup inside the water, they become very water soluble, and you can record the NMR. The NMR is very clean. So some of you who might have recorded NMR spectrum of cyclohexane, for example, you will see a very broad peak between 1 and 1.5. You cannot assign to any hydrogens, because all these things are very broad, they are connected. So it will all come here. But if you look at this, now every peak is separated, and this methyl group is all the way minus 2.5. Okay? Because this methyl group is stuck at the very bottom of the capsule, where there are a lot of 4 benzene rings. And then the other groups come slowly up, then the deshielding, that is shielding it faces, is going to be smaller. Okay, this is NMR. You know, usually we have to do a lot of other experiments to make sure how the molecule is sitting. Then we do what is called as COSI experiments, NOSI, DOSI. You know, they're all NMR experiments. You do all these things. Takes a couple of months to get everything straightened out. Okay, so basically from all the experiments, we know that the molecule is sitting like this. We know there are 2 molecules inside the capsule. This is what I told you is a 2-to-2 complex. So this methyl group is stuck at the bottom, and the other groups are sitting like this. Okay. Now, I told you before, you get, when you react with oxygen, oxygen can come from this side, pick up this hydrogen. That is, you will get this. Come from this side, pick up that hydrogen, you will get that. Or pick up this one, you get this. All 3 are possible. All 3, I told you, it happens. Now, if you put this molecule inside that a small cup, the way the molecule is sitting, based on NMR and all the other stuff, this methyl group is at the bottom, and these hydrogen and that hydrogen, these are the 3 hydrogens, 1, 2, and 3, which is almost equivalent, sterically equivalent in solution. They are no longer equivalent, because this methyl group is at the bottom, and so that is sterically hindered. And these 2 alkyl, the CH2 groups, are not the same steric. When oxygen comes in, this hydrogen will be more easily accessible compared to either of these 2. So the reaction could be selective. Okay. So this is, you can see which one is more selective by looking at the chemical shift of these things. This one is shifted by is about minus 2.6, is about 0.6, minus 0.6, this is minus 0.2. That means the more minus, it means more deeper it is. Okay. More deeper it is, less accessible the hydrogen is going to be. This is going to be the least accessible, and this one is going to be less accessible. Among the 3, this will be more accessible. So when you cannot distinguish these 3 hydrogens in everyday solution chemistry, but only with a capsule you can do this chemistry difference. So now, in principle, you should get only 1 product. Okay, afterwards the chemistry, you can put the alkene in the capsule, and then you can irradiate in water with the help of rose Bengal, and then you can produce what is called a single oxygen. It will react with the alkene. Okay, these are all details. So in solution, you get a mixture, all 3. Now in water, in capsule, now if you notice, every one of this case, the last product, this is a major product, this is about over 90%, and this is a product which is coming from abstraction of this hydrogen, which is least hindered of these 3. Okay. So we have done a number of other types of reactions and shown the molecular, when it is part of a very nano confined space, the chemistry is quite different. You can control a lot of things. Okay, this is, I don't have to tell this here to this group because you do a lot of things which is related to nanotechnology. Okay, I want to talk about the slightly different aspects of this type of chemistry. So far, what we have done is we have put this molecule inside a confined space. Okay, and then this molecule is sitting here. And there is a whole world outside. There is a lot of water outside, and there are, you can put anything else you want outside the capsule. The question is, can this molecule inside and the outside, can they interact? Can they communicate from here to there? Okay, so that's what I want to talk about for the next thing. The picture is basically like a drug dealer. You know, even if the guy sells a drug in the street and then put him in a jail, in the United States is not uncommon for a guy who is in the jail still selling drugs and then somebody depositing money in his bank account. Okay, so he can just, all through the cell phone, he can communicate, sell this, take it to that street or this street. Okay, so what we want to do is, can this same thing can happen with simple molecules? So I will talk about a couple of these things, what is called a spin and electron. So if I have a molecule which has got an odd electron, and then if I put another molecule here with odd electron, will they be able to communicate in terms of spin? Or if there is an electron transfer can occur from inside to the outside. Okay. So to give you a very, very brief introduction, I have a couple of slides. For students who might have forgotten, electrons have a spin. They have alpha or beta spin. The same thing with what we do with the NMR. Protons have also spin. That's what all the NMR spectroscopy is all about. And the electron spin, we use it for the EPR spectroscopy. Okay, so if you have a single electron, you have two spins. If you have two electrons, then you can have four spins. So a singlet, which is our two electrons have opposite spin, or the two electrons have the same spin, and this one plus or minus, this will be singlet state, there will be triplet state. Okay, this is something that you have to recognize at this stage, because we are going to talk about, use this concept as we go along. So if I have one electron, you can have alpha or beta. If I have two electrons which are in two different orbitals, then you will have four states, singlet states or triplet states. Okay. So now let's see what happens here. So basically what I want to do is, we want to put a single electron inside the capsule. I want to keep an electron outside. I want to see whether this electron knows what is the spin of the other electron, or if it changes the spin, will this do anything? Okay, so we cannot put an electron inside. So what we do is we put a nitroxide. Nitroxide or odd electrons it has got. So the nitroxide NO, this one has got a spin, and when you record the EPR spectrum, you will get an EPR for this nitroxides. So this molecule is stuck inside, and this molecule is kept outside. This is also nitroxides. This has got a positive charge. This positive charge and negative charge, there will be some interactions. So this one will stay very close to the wall or the capsule because of this Coulombic attractions. And then if you are familiar with EPR spectroscopy, you will know the nitrogen, when you have a nitroxide, when the nitrogen N14 will give you 3 lines. So if I record an EPR, you will never know whether the spectrum that you are getting is because of this or because of that. So if you want to distinguish between these two, then you will have to figure out one of them should give a different type of signal. So one way to do this is you put this inside and outside, N14 and N15. So if I have this inside as a N15, outside as N14, N15 will give 2 lines, N14 will give you 3 line spectrum. So I know if I record an EPR, I know if I get a 3-line signal, it comes from this. If I get 2-line signal, it comes from this. Okay. Now the question is, will these two interact? This N plus is very important because this plus is the one which is keeping very close to the walls. Okay. So now let's see what happens. Couple of small things before we go to the real results. This is the nitroxide. This nitroxide is water soluble because of this polar groups and the 3-line EPR spectrum you get. From this spectrum, you can get a couple of information. The coupling constant is 16.8. what is called as rotational correlation time is 0.025. This one tells about the polarity of the medium, is exactly like pyrene emission spectrum. The EPR also can tell you what is the polarity. So this rotational correlation time, it tells you about how fast a molecule is able to move around in water. So this is 0.025. So now if I add this nitroxide next to a capsule, this capsule contains something, but it is not paramagnetic, because we want to see the effect. First we want to understand where it is sitting. NOMe. Now if you look at this spectrum is changed over to this. So it is a 3 line, but then it is sort of very distorted spectrum. And then if you look at coupling constant, it is still 16.7. The rotational correlation time increased from 0.02 to 0.1. So this molecule is having a harder time to rotate because it is close to the wall, so it is not able to rotate very freely. So this number has increased. Still it is outside, still it is in water, so the coupling constant is not changed that much, 16.8 to 16.7. This is a basic thing that you use to know where it is sitting. And then we take the other molecule, this is going to go inside the capsule, and then this one, if you notice, there are 3 line spectrum. This is now, both are N14, coupling constant is 17 and this is 0.06. This is in water. And then you put them inside the capsule. Now if you look at this, coupling constant went from 17 to 15.5, so it decreased. This decrease is because inside it is not water, it is very much like benzene. So if you go back in the table, it will tell you all this. And then the rotational correlation time dropped from 0.06 to 1.4 because it is inside the capsule, it is not able to move around freely, so it is taking longer time to rotate. Okay? So from these experiments, what all we can conclude is, this molecule is inside the capsule, this molecule is outside the capsule. We cannot cut this information from the NMR because nitroxide NMR is very broad, so it is not very useful. So now we are going to change it. We are going to put this as N15, that is going to N14. So I just give you the spectrum, and then you can see very quickly. So the N4, this is the same. This part is now, since it is N15, it is giving a 2 line, and then once it goes inside, everything changes. So this is inside, this is outside. So now what we are going to do is, we are going to take this molecule and add this to this solution, and then look at the EPR. And then if you see the EPR, if there is a difference, then we will know, I will tell you what goes on. Okay. So when you add this nitroxide, this is N15, N14, then you get 5 lines, 1, 2, 3, 4, 5. This is, I have recorded spectrum slightly differently so that we can see the things, this is integrated EPR. So you get a 5 line spectrum. Now, we don't know whether these two are interacting or not interacting. In order to figure this out, what we need to do is, we need to record the spectrum of this separately, separately and add the 2 spectrum plus, and then see whether they are same or different. Okay. Okay, so we take the spectrum, nitroxide alone, inside is we put a diamagnetic compound, and then this one is close to that, this is alone, all by itself. So we record 2 separate spectrum, this spectrum and that spectrum, you add the 2, and then you compare with this. If you compare with that, as you see here, they are not identical. In principle, they should be identical if there is no communication at all between inside and outside. If there is no communication, this spectrum and that spectrum should be identical, but it is not. So obviously, there is some kind of interaction between these two. Okay, it will be. You can see it more clearly. Suppose I take a COO minus instead of the same nitroxide. We are going to keep it outside, but now if it is COO minus, it cannot go very near the capsule. So it is going to stay far away. So now you record the EPR, mixture of these two, you get a spectrum, so something similar to before. But now again, you record the 2 spectrum separately and add the 2. And then if you look at this, these 2 are exactly the same. The dotted line and the red line, they are the same. So it tells you, if this nitroxide is not very close to this capsule, they cannot communicate. It is like the drug guy sitting outside and inside. The one guy is in Waterloo, the other guy is in Toronto. There is no communication. Both the guys have to be very close in Waterloo, so for things to happen. Okay, this tells you that it is possible. There is an interaction. They know the spin of each other. Although the other one is outside this room, this molecule that is sitting here, it knows whether it is alpha or beta spin. Okay, this is something interesting. Okay, I want to go a little bit one more step. So if I take a molecule such as this one, this is the reason that we had this, all these things there. If we excite this molecule, this is going to go to the excited singlet state. This is xanthone. This is, you can excite it with the laser. And if you excite the laser, it goes to singlet state. Singlet will go to the triplet. Okay? When it goes to the triplet state, the triplet has got 3 states. It will go to one of those 3 preferentially. So it is what we call as spin polarization. Okay? So this is a time resolved EPR. This is not a regular EPR. This is you record the EPR spectrum with respect to time, with this nanosecond time scale. So now our interest is, once we excite this, there is a nitroxide that is sitting inside the capsule. They are very close. So it will quench this one. The nitroxide will be polarized. And then this one, there is another one sitting outside. We want to see whether this will also be polarized. That means it can transfer not only the spin, but it also can transfer the polarization from inside to the outside. Okay, this is basically what's going to happen here. So you excite the molecule, it goes to singlet state. Singlet state will cross the triplet state. When you read the textbooks, triplet means they will have only one single line, because at room temperature they equilibrate very quickly. Whereas by the time it is crossing, it is going to go to one of these 3 preferentially. It will not go to all 3 in equal. Okay? So if this preferential crossing, if it can be recorded by this nitroxide, then we already crossed from this place to some other place, and that place is already polarized at the very beginning. We are talking about nanosecond as soon as it is excited. And then we can transfer to the outside EPR will be polarized. Whether it will be positively or negatively polarized, it depends upon whether it goes to here or it goes to here. Okay? So let's see what happens. One more. So this is quickly to tell you, we have the xanthone excited state. This is a flash time resolved spectroscopy. So you have the absorption spectrum for this. It has a very long lifetime, triplet state. Now if you attach this tile with the nitroxide, it has the same spectrum because we are exciting this, and then it has got a very short lifetime. The lifetime is nanoseconds, because from 12,000 it came to less than 10, because it is quenching this excited state extremely fast, and it is quenching by the spin transfer from this molecule triplet to this one. Now xanthone, we are going to excite a xanthone, flash photolysis, record the EPR with respect to time, nanosecond time scales. And then I already told you, this triplet state is going to be polarized, and then we want to see whether this is polarized. If polarized means the signal will be down or it will be up. If it is not polarized, you will get a straight single line. Okay, it will be no up or down. Okay, obviously you can see already it is polarized. This nitroxide, you see a strong signal which is negative. That means one of the 3 triplet state is getting populated more than the other 2. Okay, now the question is, that is the triplet to this one is able to cross. Now we want to put something outside. Question is, will that be able to transfer to the outside one? Okay. So now, we have put this molecule outside. This is N15, this is going to be N14, and you can see already 5 lines, because now you have got this compound plus that compound. This one gives 2 lines, this gives 3 lines, so you have got 1, 2, 3, 4, 5. Okay, the inside ones corresponds to these 2, and these 2 are corresponding to this molecule. So this molecule on its own doesn't have EPR spectrum in that time scale. Okay, so now you get 3 lines, because this one came from the spin is transferred from here to here, and it is also negatively polarized because the original compound was negatively polarized. Okay, now with respect to the time, as you can see, the inside signal is disappearing, the outside signal is getting stronger, because all the spins, this came from this molecule in the excited state to this molecule is transferring the outside. So the capsule wall doesn't make any difference. If I shout louder, outside people can hear. So it doesn't have to be, you don't have to have, this wall does not make any difference. Okay. All right, so you can see it, this one. Okay, I'm going to skip a few, okay, just to make sure that, you have some confidence in what I'm talking about. As I told you before, so when you have this molecule plus nitroxide, you see a negatively polarized signal. And we change this nitroxide with a COO minus. This is going to go farther away. When it goes farther away, then polarization should disappear, because if I'm standing in the other corner, then the other guy outside may have a hard time hearing. Okay, so if you notice here, as soon as you add this one, then you don't get any signal from this. So this one, the two-line spectrum is still holding strong, and the three-line spectrum is extremely small. So the capsules, inside there is one molecule, outside there is another molecule. As long as it is close, it can transfer the information. If it is farther away, the information cannot be transferred. That's the basic thing. So putting a molecule inside the cup, it makes no difference in terms of communications, but it can make a difference in terms of, which is very important, because that's why if I want to manipulate a molecule inside the cup, I want to stand here. I cannot go inside the cup and do something. Okay. All right. So this is one thing. Okay, this one we can skip, because I want to go to the end of the talk. Okay, I will tell you a little bit something else. Okay, so far what I talked about is, okay, I hope it stays there. So we had one molecule, for example here, xanthone. I had a nitroxide inside, because I kept the nitroxide inside because I want to make sure it can transfer the signal from here to here very quickly in the nanosecond time scale. Suppose the question is, if I cut off this piece, will it be able to transfer directly from here to the outside? So I don't want to have any intermediary between myself and somebody else, the customer and myself. I want to deal directly. I don't want to have an in-between guy taking part of the money. So we are going to cut off this piece, and then now we excite this, whether it will be able to communicate with this directly. Will I be a good salesman? That's a question. Okay. Let's see. The two molecules are taken for a different purpose. This one is well known to be positively polarized. This one is well known to be negatively polarized. The question is, will there be negative and positive? If I can see that, that means there is some success in the whole thing. Okay, this one is telling you, we will go to the result. Okay, this is all these details. Okay, this is okay. All right, this is for the students. This is something that what I'm talking here. Normally, when you go and record the NMR or EPR, what you are recording is a very small difference in the Boltzmann distribution of the spins between the lower state and upper state. We all study these things in physical chemistry or even on organic chemistry. What I am talking about is, this one is already disturbed because we are exciting the molecule. We are letting it cross from the excited singlet state to the triplet state. When it does cross, it doesn't have a distribution like this. When it crosses, depending upon the system, the bottom one may be more populated, or the top one may be more populated. Depending upon which one gets populated more, either you will get this one, eventually it is going to reach this situation within a few nanoseconds or within a few seconds. So as it reaches that, then the signal will become very weak. At the very beginning, you will get a very strong signal. So if it crosses to this, you will get a positive, and if it is like this, you get a negative. The two molecules I showed you, one of them will be like this, another one will be like that. If I get these two in different way with the two different molecules, then we can trust all the thing I'm talking about. Okay. So we put with the benzyl inside, excite directly the benzyl with a laser, and then we record the EPR. As you see here, this signal is coming from the nitroxide, which is outside. The nitroxide signal is positively polarized, which is well known. The benzyl in the excited state is positively polarized. That polarization is transferred to the molecule that is outside. Similarly, if I go to this molecule, that is xanthone, which is, as you see here, there is no more this intermediary here. We are directly dealing between this one and that one. This is the plant and the customer. There is no intermediary shop here. So this is go directly from here to here. It is negatively polarized. So you can see they can communicate between inside and outside. Okay, this is a very small difference, which is the spin of the electron seems to know what is the spin outside. So they can manipulate these two. Okay. All right, so this one, I want to tell you a little bit about, maybe another 5 minutes, how to control, for example, electron transfer. This is a lot more important in terms of applications rather than spin. Spin could be important, but not right now, but it may be in the next 20 years. People will try to manipulate the spin, which may become part of the cell phone. Who knows? The microwave technology, which was invented about 50 years ago, now we are using it as in cell phone technology. So this spin transfer, because it is tiny manipulations of things. So what we are going to do, we are going to excite one molecule. We are going to make this guy a little bit unpleasant, and then when he is unhappy, will it give up something to the outside? That is electron transfer. So this is the donor, this is the acceptor. Excite the molecule. Can it transfer the electron in spite of the wall between inside and outside? For example, for electron transfer, energy transfer, they have to be very close to each other. There should be nothing in between them. Okay. All right. So let's see what happens. We use these various things like some of these molecules. You don't have to remember. Basically, these are all donors. These are all acceptors. We are going to excite this molecule, and when it is excited, this molecule is going to be inside the capsule. This molecule is going to be outside the capsule. If you notice here, they all have positive charge. So that is what is going to keep it stuck to the close. These molecules are hydrophobic. They go inside. And then we want to watch what happens when we excite these things. There is no more spin. There is only electron. The electron is going to go from inside to the outside. So you will get radical cation, radical anion. So this is the molecule still being inside. You see a good, nice fluorescence spectrum. And the lifetime is about 2 nanoseconds. Okay, now if you add this molecule outside, which is a straightforward methyl viologen, 2 cations, so that will make it close to this capsule. As you keep adding, the fluorescence is getting quenched. That means something is interacting between this and that. That is why the fluorescence is coming down. So we don't know exactly what is coming, why it is happening, but certainly there is a communication between these two. Okay, so you can add the other one, like the simple molecule like pyridinium cation. Again, the same thing happens. Okay, now we know for certain, still being inside, molecule outside, they seem to interact. What happened to these things? So if you want to figure out what is happening, so you record as soon as you excite the molecule, what would happen is, if there is an electron transfer, this will lose an electron, it will become a radical cation. This will accept an electron, this will become a radical. So if you record the spectrum of this, you can see you have a spectrum corresponding to the radical cation. This is a spectrum which is radical cation spectrum of Stilbene is known. So we record the spectrum in the nanosecond, microsecond time scale. So basically what happens is electron is transferred from inside to the outside, and you can get the spectrum for this. And the other things are all supporting data. So basically what is going to happen is, after it is transferred, this electron will come back, because it cannot remain as a radical cation and radical forever. So it is going to come back. When it does come back, the signal will, this radical cation signal intensity will come down, and the Stilbene signal will get back. Okay? So it does happen. Okay, I'm going to show you. So for example, I showed you the radical cation spectrum of Stilbene is happening. The outside molecule in the one I had earlier was pyridinium, methyl viologen. Sorry, pyridinium cation. Pyridinium radical signal, unfortunately, was far away from our instrument range. So we went back to this methyl viologen. And methyl viologen, when it accepts an electron, it will become a radical. This will become a radical cation. So radical cation. So if you notice here, we see a radical cation spectrum for methyl viologen and the radical cation spectrum for Stilbene. It clearly tells you there's an electron transfer from inside to the outside. Okay, so there is no problem with respect to electron transfer. The more important interesting thing is, after it transfers the electron, this electron has to go back. In this particular case, it takes about 4.6 microseconds. In the other case, it's about 20 nanoseconds. This charge separation, for example, people who do dye sensitized solar cells, the most important thing is keep this charge separation longer. The more you can keep it, more you can manipulate these things. But in solution, All these things will happen in almost picosecond time scale. But here, as you notice here, it is taking about 5 microseconds for this electron to get back from here to inside the capsule. So going back is slow, and the forward, which is excited, it is not that slow. In fact, one of my students is spending time in Clemens Burda's lab at Case Western to measure these things in femtosecond time scale, because we tried a picosecond, it is faster than that, so we don't have the facility, so she has gone there to do these experiments. To finish it up, I just want to show you one small applications of why we do this sort of stuff. So for example, people who do titanium dioxide, the solar cells, they have titanium dioxide. This is common. And then you put a dye on top of it so that the dye can absorb all parts of solar radiations. And then this will absorb the light and then transfer electron from here to here, and this will become radical cation and then radical anion. These electrons will eventually come back. That is what I told you, that is the one which generates electricity. Okay? The problem with this, well, there is a lot of, Michael Gratzel has done this 20, 30 years ago, but still people today, thousands and thousands of people do this project because they want to make the system much better. The problem is, if you put a dye on titanium dioxide, there are a couple of things. One, it doesn't stick very well. Second, they aggregate. If they aggregate, that means excited state get quenched by without electron transfer. Oftentimes, they degrade by themselves. Okay? So the other approach what people do is, you put some kind of acid groups so that you can stick the dye onto the titanium dioxide. Other thing is, when you put the legs, you put the leg far apart, then you can separate the dyes. So that way you don't have to, aggregation you can stop. But then each time you change a dye, you have to put a different leg. So that means it has become a synthetic project. So what you can do is, you can put the dye inside the capsule. The capsule has already acid groups. So the capsule, you can stick it onto the titanium dioxide. You excite this, there is an electron transfer from inside to this one, and then I already told you going back is slow. So this is exactly what you want. Okay, we wanted to show whether it is really happens. So we took some of these dyes. These are the standard dyes people use. So we put it in. Okay, this one, this tells you this is happening. The next one is more important. Okay, we take this octa acid. This is our the capsule. IR spectrum looks like this, the solid samples. We take the capsule containing these dyes and coat it on the films of this titanium dioxide. Then you can still see all these things, peaks are here. This is the titanium dioxide. The bottom one is zirconium oxide. So we take this as a control. This is not a semiconductor, this is a semiconductor. So we wanted to compare this, what happens. So you can coat this capsule onto the titanium dioxide film or onto zirconium oxide film. And then if you irradiate this, okay, for example, as you add, this in this case colloidal, the emission is getting quenched. That means the electron is getting transferred from this molecule to that molecule. This molecule is inside the capsule. And then if you add zirconium oxide, then there is no quenching because zirconium oxide doesn't accept electrons. So now if you put the whole thing, for example, on the film, you can see here in the case of titanium dioxide, it is completely, there is no more emission. In the zirconium oxide, there is still emission. So that means the guest molecule, which is the dye molecules, which is inside the capsule, is transferring the electron to titanium dioxide. The rest of it is all, it is all engineering and technology and all this sort of stuff. So at least we are able to show that is something that is worthwhile pursuing this project. Okay, so this is the basic thing. Finishing up, we can carry out electron transfer from a molecule that is capsuled to the surface, and this encapsulation, it helps to slow down the back electron transfer. Okay, so I have tried to show you that communication is possible. The work that I talked about is done by 3 people. Mintu is a graduate student. Shipra is another graduate student. She is from IIT Delhi. She is from IIT Guwahati. She is the one who did a lot of this time-resolved EPR, time-resolved electron transfers thing. She is the one who is at Case Western trying to do these experiments in a much shorter time scale. Nityanandan is a postdoc. who characterized and then made sure everything is, all this encapsulation and NMR and all these things he did. The time resolved EPR, we don't have an instrument, so we did the work in Professor Turo's lab, and Stefan Jakush is the person who helped with all these details about experiments, because some of these sophisticated instruments we don't know how to use, so somebody has to help with all this stuff. So this is with that. I'm going to stop. Before I finish, I just want to tell you something. We all do, what I do is basic science. It is not applied. I'm not a guy who can make money out of what I do. But I think it has some value, because I just want to show you a quote by somebody from England. This is, there is Hardy, is a very famous mathematician. I don't know whether your Hardy's name is, in 1920s and 40s, a big guy. He has written a small book, Mathematician's Apology. Okay, so a lot of people asked him, "What's the big deal? About you have been so famous at Oxford, I guess, and then you have done a lot of maths, and everybody says you are a big guy. So what's the big deal about what you did?" Okay, here he says, no discovery of mine is likely to make at least the least difference to the amenity of the world. I have helped to train other mathematicians of the same kind. Their work has been as useless as my own. This is, Hardy is a very famous guy. Anyhow, I have added something to the knowledge and helped others to add more. These have a value. So basic science, what he is trying to sell, the importance of basic science. And then, I don't know whether you know, Hardy is more known, he's a very famous mathematician of that century. Okay, he's the person whom he discovered is Ramanujan. He is one of the Indian mathematician. There are lots of books and movies about him. He's a poor guy. He went to school. He flunked every exam possible. So he never graduated from college. But then, he used to have, he'd look for jobs. He could never get a job. So what he used to do is he used to write a problem by himself and solve on the bottom. He never had anything in between. Okay, so he's a very outstanding mathematician of this century. He died at the age of 30 or 31. And then at that time when he was doing all this stuff, nobody thought this guy has, he's just living in a very miserable conditions. And in those days, India was, Britishers were there. So he used to go to everybody, show them this piece of paper. So nobody understood what this guy is talking about. So they told him, "Why don't you send these papers to people in England, Cambridge, Oxford, Imperial College?" So he kept posting these things. Only Hardy was the only person who replied to him. And then, because he looked at these things, he thought this guy must be a genius, or this guy must be an idiot, one of these two. So he wanted to check him out. So he sent a cable to the British consulate. He bought the ticket to him, and then he took him to Oxford. They published number of very important papers. Those are the papers plays a key role in computer programming today. And then those are the ones which control, for example, airport, this flight control and all this stuff. Because this is done by Ramanujan. He was 31, 32 years old when he died. And then, he did all this stuff without learning maths from anybody or any schools. He just somehow it all occurred to him. So it is, in a way, all what we do could be useful. So I think with that I will stop. Okay. Okay.
Very much. Time for questions, if there are any. John?
Okay. So, but if you look at the interactions, they're positively charged outside. Mm-hmm. Those things they stick to those things because of very strong Coulombic interactions, plus and minus. So if you increase the concentrations, you can see more and more will come and stick to these walls of the capsule, and then you can figure out some of these things by NMR, because NMR, the proton relaxation time, is controlled by the nitroxide. So we record the NMR of all these hydrogens, the relaxation times, And then from that, I can tell where the nitroxide is sitting. It is sitting here or here, or it is controlled by the distance and all that stuff.
Because you might have a distribution of some capsules.
No, yeah, there could be a distribution, but the thing is, the ones which are very close, those are the ones going to be doing the job. So the ones which are far away, it's not doing much. So if you take a nitroxide without any plus or minus, right, then they are widely all over the place. So there the effect is much smaller. Okay.
Very nice presentation. So this NMR that you presented in the capsule, the molecule in the capsule, is still being able to be sensed by this magnetic field, right? So, but if the capsule is thicker, like in the micellar system, it will not be visible.
Okay.
So you want to comment on that? What is the thickness of the capsule above which you will not be able to see the proton?
No, I think, okay, micellar cases, the problem is the micelles, standard ones are sodium dodecyl sulfate or hexadecyl trimethylammonium chloride. They are themselves have a lot of CH2, 20 of these things. So you are going to have a huge signal because of that. Okay, and then in these ones, they have aromatic groups. So when you put another molecule here, this aromatic ring current is going to have an effect on the NMR signal of this. Effect shifts the whole things upfield. So it separates the guest from the host. The host peaks are all staying close to 5 and above. The guest peaks are all going below 0. So that's biggest advantage of that. The thickness does not make any difference of this capsule. Yeah.
So I'll try to add some polymer knowledge to your system.
Okay.
I think your encapsulated gas host system could be very interesting, for the polymerization. One system you already have a nitroxide radical trapped inside. So nitroxide radical is kind of reagent for the living polymerization.
Yeah, correct.
So to see what happens, quite interesting. And there's other possibility for the initiative. I think this could be interesting. I'm not sure whether you're interested in this, but from polymer perspective, I think it could be very.
No, if you think it's interesting, I could get interested. If I don't know much about polymers, but
it's not for fundamental, it's not for industrial applications. So we difficult to get the money.
Yeah, I'm not opposed to getting money.
Yeah,
but I don't know how to get it.
So it could be very interesting in polymer science from my perspective.
Perhaps I can ask one. You showed an example where the confined molecule failed to dimerize.
Yeah, correct.
That was different from a non-confined space. Has the opposite tactic been employed so that in these confined spaces you can actually make molecules dimerize? That wouldn't
correct.
And use it practically as a means of synthesis.
Yeah, correct. It can be. So for some of the molecules, for example, they don't want to dimerize because they undergo, for example, you take steel beans. One of the most common reactions of them is rotation. They rotate. But we have done, for example, some smaller systems, they normally will undergo what is called cis-trans isomerization. That is the most common reactions of steel beans or any kind of olefins. But once you put it inside, if the space is, if the two molecules are sitting inside, there is not enough space for them to rotate.
Yeah.
So then they will just form the 2+2 cycloadditions. Yeah.
So is that a practical significance?
Well, practical is, you can do it practical. You can make these molecules and for regular synthesis purposes. Most people who do synthesis, they do in natural product synthesis in milligram scale. So for that kind of thing is okay. If you are talking about a plant or something, it is not, because these things are, making this capsule is pretty expensive operation. Yeah.
Okay, if there are no further questions, please join me in Dr. Ramamurthy. We're very impressed.
Okay, thank you.